Hello friends, welcome to this next video on Lebesgue measurable functions. Okay, so we have seen that continuous functions are Lebesgue measurable functions, and then we have seen that monotonic functions are Lebesgue measurable functions. Monotonic functions are Lebesgue measurable functions, right? Now we would like to see, these are the basic things which automatically should come to our mind, that whether if we have two functions f and g, whether their sum is Lebesgue measurable function or not. Okay, and if we multiply a Lebesgue measurable function with a constant, whether that is a Lebesgue measurable function or not, and if we have a product of two Lebesgue measurable function, that is Lebesgue measurable function or not. Similarly, composition of two Lebesgue measurable function or not. Things like that we need to look at, right? Similarly, division of two functions, Lebesgue measurable function, whenever the division is possible, that is Lebesgue measurable function or not. Okay, so these are the things we want to look at, but there is a problem with these things. The problem comes from the fact that we are defining our function to be from some domain E to extended real numbers, right? So it means that our function can take at certain point value, say plus infinity, and suppose the other function g also takes the same value at the same point, or minus takes the opposite sign with infinity. Okay, so what will be f plus g at x1, right? That will be infinity minus infinity, and that is not defined form, undefined form, right? So it means that if you are defining your function from a certain domain E to extended real numbers, then there is a problem when you add two functions. You have to function f and g both defined from E to extended real line. Okay, then there may be a problem if at certain point in E, say at x1, both your f is taking the value infinity or minus infinity, and g is taking the value infinity with opposite sign, right? In that case, it is not possible for you to define f plus g at x1. So what to do? Okay, so similar problems can occur in these all these cases. Okay, so we have to deal with this problem, that if your function is from some certain domain to extended real line, which we are doing right now. We have defined our functions before starting with Lebesgue measurable functions. We have declared this thing that our range will be now extended real line, right? So how to deal with this situation, that at certain points your function f plus g may be undefined. Okay, it is infinity minus infinity form, which is undefined form, right? So to deal with certain these situations, we have a theorem which will help us in figuring out that how to tackle with these difficulties. So in this video I'll just prove that theorem, and in the next video we will try to use that theorem to make sense that our f plus g is actually valid everywhere, or something like that we will do. Okay, so let us write down that theorem, and let us write the proof for that theorem, which will be useful for us in tackling this situation. Okay, so what is that theorem? First of all, I'll just write down the theorem. Theorem says that let f be an extended real valued function on E function on E. Okay, so we have first part says that if f is measurable on E, if f is Lebesgue measurable function on E, and f is equal to g almost everywhere on E. Okay, now you must be knowing what is almost everywhere, we have used it many times. Then g is also Lebesgue measurable function on E. Then g is also Lebesgue measurable function on E. Okay, and the next part of the theorem says that for a measurable function, a measurable subset D of E, for a measurable subset D of E, f is Lebesgue measurable function. F is Lebesgue measurable function if and only if restrictions of f to D and E minus D, restrictions of f to D and E minus D are Lebesgue measurable functions. So let us prove this thing. Okay, so let us look at the first part. We have this situation that you have a domain E, okay, and f is Lebesgue measurable function. It means that its domain is Lebesgue measurable set, that is E is a Lebesgue measurable set, right? And we want to prove that G is also Lebesgue measurable function where f is equal to G almost everywhere, right? So you just define a set A. A is that part of E on which f and g are not equal. F of x is not equal to g of x. So basically here you have, this is your E and this is the part A, right? Now because you are given that f is equal to g almost everywhere, it means that measure of the set where f is not equal to g is 0, right? Now because f is equal to g almost everywhere, f is equal to g almost everywhere implies measure of the set A is 0, right? Okay, and now can you look at for any number C, what is this quantity? X belongs to E such that g of x is greater than C. Now see, on this part, E minus A part, f and g are actually same, right? And on A part, f and g may not be same. So I am writing it like this: x belongs to A such that g of x greater than C, union with x greater than x belongs to E minus A such that g of x is greater than C. I have done nothing, I have just written it in two parts, okay, because A and E minus A they are actually disjoint, so I can write it like this. Okay, now keep this part as such. This is equal to x belongs to A such that g of x is greater than C, union with, on this set x belongs to E minus A, on this set E minus A, f and g are equal, so I can replace g with f, right? This is because on E minus A, f is equal to g. Okay, right. Okay, so this, keep the first set as such, x belongs to A such that g of x is greater than C. Now can you look at this quantity? I can write it as union with x belongs to E such that f of x is greater than C intersection with A, right? So what I am doing, I wanted to look at those points in this set E minus A, this part, outside part. This is your A, this part is your A, right? I want to look at this part outside A and I want to find out in this part which points, at which points the function fx is greater than C. So what I can do, I can just, I'm sorry, I have written something wrong here. Here it should be E minus A. Okay, so what I am doing, I am collecting all the points of E where fx is greater than C, and then I am taking the intersection with E minus A. In that way, I will get that part of E minus A where f of x is greater than C, right? So I will write it neatly so that the things are clear. So I will write it like this: x belongs to A such that g of x is greater than C. That is the first part, no problem. Union with x, I should write it a square bracket maybe, x belongs to E such that f of x is greater than C intersection with E minus A. Right. Now can you look at this set? Is this set Lebesgue measurable set? You can see that this is actually a subset of A, right? And we have already seen above that measure of A is 0, and we know that every subset of a set with measure 0 has a measure 0. So it implies that this particular set, I'll call it star, so it implies that measure of star is 0. It implies that star is a Lebesgue measurable set. So this first set is actually a Lebesgue measurable set, right? Now what is this set? This is a set, again Lebesgue measurable set. Why? Because f is given to be Lebesgue measurable function. So by definition of Lebesgue measurable function, this set has to be Lebesgue measurable set. Now what is this? This is actually E intersection with A complement. Now A is Lebesgue measurable set because it has major 0. So A complement is a Lebesgue measurable set, and also E is a Lebesgue measurable set, and we know that intersection of two Lebesgue measurable set is a Lebesgue measurable set. So this set is also a Lebesgue measurable set. So you have two Lebesgue measurable sets, their intersection is a Lebesgue measurable set, and then their union with a Lebesgue measurable set is a Lebesgue measurable set. So overall this set is a Lebesgue measurable set, right? So what do we get? We get that if f is equal to g almost everywhere, right, then x belongs to E such that g of x is greater than c, right? This is a Lebesgue measurable set for each real number c, right? Moreover, E being the domain of f is already Lebesgue measurable set. Therefore, by definition, g is a Lebesgue measurable function. So in this way we prove the first part of the theorem, right? Now let us prove the second part of the theorem. That is quite simple. So second part of the theorem says that for any measurable subset D of E, subset D of E, f is Lebesgue measurable function if and only if restriction of f on D and E minus D are Lebesgue measurable functions. Okay. So let us try to prove this. So this is actually quite simple. You can just write, you can note this thing. So I have this, I can draw a figure. This is your set E and this is your set D, right? This is measurable and E is measurable, okay? That is given in the statement, right? So I can write actually for any number C, for any real number C, you can write this set x belongs to E such that f of x is greater than C. You can write this quantity as, you can collect all those points in D for which f of x is greater than C, and then take the union with all those points in E minus D for which f of x is greater than C, right? Now we have to prove this thing. So first assume that if restrictions of f on D and E minus D are Lebesgue measurable functions, then by definition this set is Lebesgue measurable set and this set is a Lebesgue measurable set, okay? Then both sets on right hand sides are Lebesgue measurable set, and hence their union is a Lebesgue measurable set. It implies x belongs to E, f of x greater than C is Lebesgue measurable set, which implies that f is Lebesgue measurable function. Here I am just applying the definition of Lebesgue measurable function. Now let us assume the converse. Now let f is Lebesgue measurable function, okay? Then it implies that this set x belongs to E such that f of x is greater than C is Lebesgue measurable set. Now how can you write this set? Look at this set, x belongs to D such that f of x is greater than C. You can actually write this set as x belongs to E such that f of x is greater than C intersection with D, right? Now this set is Lebesgue measurable set because f is Lebesgue measurable function, and this set D is given to be Lebesgue measurable set, and we know that intersection of two Lebesgue measurable set is Lebesgue measurable set. So this whole set is a Lebesgue measurable set, which implies that restriction of f on D is a Lebesgue measurable function. Similarly, x belongs to E minus D such that f of x is greater than C. You can actually write this set as x belongs to E such that f of x is greater than C, and then its intersection with E minus D. On the similar lines, this set is a Lebesgue measurable set, we have proved above already, because this is nothing but E intersection D complement, and both E and D are Lebesgue measurable set, and this is Lebesgue measurable set by the definition that f is the Lebesgue measurable function. So this whole set is a Lebesgue measurable set, which implies that restriction of f on E minus D is a Lebesgue measurable function. Okay, so in this way we prove this proposition. In the next video we will see that how can we use this proposition for defining f plus g when your f and g are extended real valued functions. Thank you.